This problem and all other practice problems for Calc 2 here at Rutgers can be found in Sarai Studies. A link is in the description box below. Does the following series converge or diverge? We're going to be using the limit comparison test in this video because in the last video we tried doing the same problem using DCT, the direct comparison test, but we got a little stuck over here because the comparison wasn't as easy as we thought it was going to be. So I told you that as soon as you feel like the comparison is a little bit hard, try LCT because it might be easier. So that's what we're going to do here. So the test that we're using is LCT, and the rule is based on the following. So in the limit comparison test, we find the limit as n approaches infinity of a of n over b of n, and whatever that limit is, that L, or in this case rho, pronounced rho, spelt rho, R-O, based on what that is, we can make some conclusions. So, by the way, Molnar uses rho. We don't say p, we say rho. Someone 5 billion years ago, I don't know, came up with rho. We don't know. Some people use rho, some people use L, whatever floats your boat. I'm going to be consistent with Molnar and use rho. So the rule here is there's 3 rules. I like to start with the bottom 2. So p is equal to 0, p is equal to infinity. If the series b of n converges, diverges, then so will the series a of n converge, diverge. And then the first rule is a little bit different. So this one is if p is basically not equal to 0, so a non-zero number. If that's the case, then whatever the series b of n is, then the series a of n will be that exact same thing. So if the series b of n converges, then so will a of n. They will both be the same. So notice that the series b of n is what controls the behavior of the series a of n. Alright, so DCT was IBBCC. LCT is IBB LC. So it's literally just one letter difference, and it's easy to remember because L, limit comparison test. So this one is going to be LCT, this one's going to be DCT. The only difference is that instead of comparing, we're taking the limit. So I stands for information, the information that we know plus the information that we need. So it's just like DCT, A of n is a sequence that they already give us. B of n is what we need, which brings us to the second step, which is B, find B of n. How do we do that? We take our given sequence A of n, and we ask ourselves, at large n, so as n gets really, really big, what does this eventually become? So as n approaches infinity, what becomes insignificant? Well, I would say that adding a 1 when n is infinity and adding a 3 is not going to make much of a difference. So those would become insignificant. So I would say this becomes square root of n over square root of n squared. And so that's my b of n. I'm going to plug that in there. Which brings me to step 3, which is B, but this B stands for find the behavior of the series B of n. The reason we care about this is because the series B of n, its behavior literally determines what the series of A of n is going to do. So we need to find what it's going to do. So we have the series from n is equal to 1, because I see n is equal to 1 here, I put it here, of B of n. In this step, you will always do the geometric or the p-test. So you have to get it into one of those forms. So simplify, this becomes n to the 1/2, this becomes just n because these cancel out. And if you do 1/2 minus 1 because of the same bases, you will get negative 1/2. So this is really just 1 over n to the 1/2. And that is your simplified series, which I see that it's in the form of 1 over n to the p, where p is equal to 1/2. So I'm going to use the p-test. The way that I remember the rule for the p-test is the movie rating PG-13. So p is greater than 1, forget the 3, convergence always comes first for both the geometric and p-test, and so then the opposite is true. Given that p is equal to 1/2, it's obviously going to be smaller than 1 because you're dividing 1, so obviously it's going to be smaller. We know that this series b of n is going to diverge, so our little sentence is going to say that this series b of n diverges, and so we have this condition here is met, and also we have that this diverges. Now, depending on what rho is, we're going to have a certain conclusion. So we need this part as well. That is where the L part comes in, and that's finding the limit. So we have the limit as n approaches infinity of A of n, so we take this, over B of n, so we take this. But a lot of professors actually skip this step. We never write it this way. I never write it this way. Another way that you could do this is literally just take B of n and flip it and multiply instead. So I'm going to take this and just flip it, and then I never have to deal with that ugliness. So essentially, instead of doing this, we say limit as n approaches infinity of A of n times the reciprocal, which is 1 over B of n, right? So now we just have to find this limit. Remember, this can be simplified to just n to the 1/2, which is essentially just n to the 1/2. So this becomes the limit of the square root of n, because that's what this is, square root of n, times square root of n plus 1 over the following. When we multiply these together, that just cancels out to be n, and then plus square root of n, right? Because this over here becomes this, which is just n squared, and these cancel out and we're left with n. And now we have a nice simplified rational fraction, and we know that we can divide every term in the fraction by the term with the highest power in the denominator. So in that case, that's going to be n squared. Now this is interesting because this is under a root. So for these, you can divide every term by just n squared, but then in the numerator, you divide by root n squared. This becomes 1. This is just n, which becomes 1, and this is just n. So now we have the limit as n approaches infinity of 1 plus square root of n over square root of 1 plus 3 square root of n, n squared. And then when we plug in infinity, infinity squared is just infinity. These go to 0, and so we're left with 1 plus 0 over square root of 1 plus 0, which is just 1 over 1, which is 1. So we have that rho is equal to 1. By the way, this is not the same thing as like the p-test. Like p in the p-test and this p that's not really p, it's rho, are not the same thing, okay? So p is equal to 1. That means that we have that p is equal to a non-zero number, so it's not infinity. And because this is true and this is true, then we can say that the series A of n is doing whatever the series B of n is doing. So it's also going to diverge. So when rho is a non-zero number, for example 1, then whatever the series B of n is doing, the series A of n will also do the same. And so we can say that our series A of n diverges. And that brings us to our last step, which is our conclusion, where we put everything together in a nice, beautiful sentence. Since, and I go in the order by my work, so blue and then green, the series n is equal to 1 to infinity of 1 over n to the 1/2 diverges by the p-test, where p is equal to 1/2 and is less than 1, so that's this blue part, and then the green part, the limit as n approaches infinity, and I literally just write this here and what it's equal to. And I say it's equal to 1, which is not equal to 0, so it's a non-zero number. So this is our green part right here. Then the LCT, the limit comparison test, implies that the given series from n is equal to 1 to infinity diverges as well. And that's our yellow part. So make sure that your conclusion has your 3 main things, your answer, and your justification for that answer.